Okay, we're back here. It's Monday. We're going to be finishing up our first set of notes from chapter 19, which deals with heat, work, and the first law of thermodynamics. Okay. And on Thursday, we defined work. We calculated work done on and by a gas, and then we calculated work for ideal gas processes. So now we're ready to use our knowledge of work, and we're going to study the first law of thermodynamics, which is just conservation of energy to include heat and work. So let's get started. So we saw in Thursday that there's two different ways we can change the energy of a system, right? So here's, for example, water. You can heat the water, which will raise its thermal energy. The molecules are moving faster, they're colliding more, they have more thermal energy, and macroscopically that gives rise to an increase in temperature. You can also do work on the gas, for example, turning the paddle, and that work can be used to increase the thermal energy of a gas. So these are completely equivalent. There's two different ways that we can change the microscopic energy of the gas, and that's by heating it or by doing work on it. And so if we put these results together, so we can change the system's energy by heating the gas, I'm saying gas, but any system, or doing work on the system. So where does that go? Well, some of the work or some of the heat added can go into increasing the mechanical energy, and that's just what you studied in 1150. That's kinetic and potential energy of the macroscopic body. We're more interested in this chapter with the microscopic energy, and that's the thermal energy of the gas, and that depends primarily on the temperature, which is related to how fast the molecules are moving around. And so for this chapter, we're going to consider cases where the mechanical energy, the macroscopic energy, is not changing. In other words, the system as a whole is not translating or rotating, and its potential energy is not changing. So we're going to set that equal to 0 for this chapter. And what that says is that the work done, the external work done on the gas and the heat added, when you add these two contributions, that leads to the change in the thermal energy, or in simple words, it changes the temperature of the system. Okay? And if we know how the temperature changes, and we have other equations which relate temperature to the other state variables like pressure and volume, so for example, the ideal gas law, we can use that equation to calculate how the other variables like the temperature and the pressure change. So here's a quick summary of the sign conventions here. And this is the hardest part, is just keeping track of the signs. And so here's our system. So let's just pretend it's a gas in a can, okay? Or a gas. Let's better example. How about a gas with a piston enclosed and acting on it? So in this case, if the work done on the gas is positive, that means that the gas is compressing. The external force is in the same direction as displacement. And so positive work done on the system, so external work is positive, that increases the thermal energy. So in other words, you compress a gas, that will tend to heat up the gas if the heat transfer is 0. On the other hand, negative work done externally on the gas, or positive work done by the gas, means that the external force and the displacement are in opposite directions. So in other words, the gas is expanding against this external force. That's a negative work done on the gas, and that would be an expansion. Okay, so positive work done on the gas is a compression. Negative work is an expansion. Heat positive heat. Heat is positive if heat enters the gas, meaning the temperature of the surroundings is higher than the temperature of the gas, and the heat term is negative if heat energy escapes from the gas, okay, meaning the gas is at a higher temperature than the surroundings. And again, I'm saying gas, but this can apply to any system. We're generalizing it so far. And so when you add these contributions, the work done, external work done on the gas, plus the heat added to the gas, those two add up to the change in the thermal energy. And right now, we're assuming again that the mechanical energy is not changing, because otherwise some of this heat and work can go into changing mechanical energy. And so that's what we're assuming here, is that the change in the mechanical energy is zero. So let's just do a little bookkeeping here, an example with signs. So in part A of the figure, this system gains 1,500 joules of heat, and 2,200 joules of work is done by the system on its surroundings. Okay, start with that. And if what that means is that if the system is doing 2,200 joules of work, it's expanding, that means that the external work done on the system is negative 2,200 joules. So when we add these two up, Q is 1,500 joules, W external is negative 2,200 joules, and that means that the change in the thermal energy is negative 700 joules. So, in other words, the gas is expanding and it's cooling, a decrease in the thermal energy. So now in part B, suppose that the system gains 1,500 joules of heat, but 2,200 joules of work is done on the system. And what that means is that the external work is positive 2,200 joules. Positive external work, meaning that the force, the pushing on the system, is in the same direction as displacement. In other words, the gas is compressing, or the system is being compressed. And so that means positive external work. And when you add these two together, in this case, positive 1,500 joules, heat is entering the system, positive 2,200 joules of work, the gas is being compressed, positive external work, the change in the thermal energy is 3,700 joules, which means the system is heating up. So typically, gases, when they're compressed, tend to heat, and when they expand, they tend to cool in most cases. So let's look at the first law of thermodynamics. We discussed some processes earlier in the chapter. We're going to discuss this adiabatic process a little bit down the road here. So let's apply the first law to each of these. So for example, the first one, an isochoric process. Remember, that's a process at constant volume. And you can think of this as a rigid container of gas. And if the volume is not changing, then the work done on the gas is zero, right? Because there's no displacement. Volume isn't changing. So W external is zero. And when we go back to the first law of thermodynamics, if you substitute external work as zero, that means that all the heat added goes into changing, or removed, goes into changing the thermal energy of the system. So in other words, heat added to the gas increases its temperature, heat removed from the gas decreases its temperature. So that's a constant volume process. There is no net work done on or by the gas. Okay. Second type of process that we studied is called isothermal process. Okay. And that's a process that's carried out at constant temperature. And if the temperature is constant, then there's no change in the thermal energy of the system. So delta E thermal is zero. And so in this case, the heat added plus the work done on the gas has to add up to be zero. And so that means that heat and work are the same magnitude, but they're opposite signs. And so, for example, if heat is added to the system at constant temperature, Q is positive, which means that the external work must be negative, which means the gas must be expanding. And so at constant temperature, all of the heat goes into expanding the gas. Okay. If Q is negative, meaning heat is flowing from the system to the surroundings, then W external must be the same magnitude but a positive number. And in this case, positive external work means the external force is in the same direction as displacement, which means the gas must be compressed. And so, in other words, the gas is being compressed and an equal amount of heat as work leaves the system, so as to keep the temperature constant. So that's an isothermal process. In this case, we set delta E thermal as 0. The third type of process is one which is isobaric, and that's carried out at constant pressure. And so in this case, the work is just equal to P times delta V. We found that out earlier. And so in the heat added minus P delta V is delta E thermal. So in this case, there really isn't as clear cut of a picture as the other two. None of the terms are 0, but you get a pretty simple relation where if I know 2 of these 3 variables in this, or 2 or 3 of these terms, I can calculate the other. The last process that we're going to cover, and we haven't done anything with this yet, is called adiabatic. And this is a process which is done in which no heat is added to or removed from the system. And in this case, Q is 0 because no heat enters or leaves. And so the first law of thermodynamics says that all of the work goes into changing the thermal energy. And so, for example, if no heat is added or removed from the system, and the external work is positive, meaning a gas is compressed, then delta E thermal is positive, the temperature will increase. So in other words, you compress the gas or the system, and all of that goes into heating up the system. And there's 2 practical applications of adiabatic where it's a good approximation. The first one, if you've done chemistry, you might have done where you did the specific heats, the heat capacities, and you had the insulated styrofoam container. And so in that case, if the gas or the system is insulated, then the heat enters or leaves only very slowly, and we can approximate it as 0. The second is if the process is carried out so fast that the system doesn't have a chance to transfer heat to the surroundings. And this could be an atmospheric air parcel going over a mountain, and we'll deal with that in a little bit. So, in other words, if we know the equations for the first law for any of these processes, we can combine these with the ideal gas law, and we can determine how the pressures, the volumes, and the temperatures, the state variables change as the system goes through the process. So in one of your homework problems, you're going to be dealing with these first law bar charts. Your author likes these, and they're a good intuitive picture of what's going on here in the process. And so we have the first law of thermodynamics, which says W external plus the heat added or removed, Q, is delta E thermal. And we can write that as E final minus E initial. So we can add E initial to both sides, and the first law of thermodynamics can be written in this way. The initial thermal energy plus the work done on the system, W external, your author refuses to use external, plus Q and that's equal to the final thermal energy. And we can write this as a bar chart. And so here's an example with an isothermal process. Okay, so isothermal means no change in temperature, which means that the thermal energy is constant. Okay? So in the bar chart here, what we can draw is we can draw the heights of the bars for the initial thermal energy and the final thermal energy. They're the same height because they're the same. It doesn't change. Now, since they don't change and the sum of the three bars on the left-hand side has to equal the bar on the height of the bar on the right, that means that the magnitudes of Q and W external must be the same, but they must be opposite signs. So in other words, these two add up to be 0, so that the initial and final thermal energies are constant. So what's going on in this process? Well, Q is positive, which means heat is being added to the system, but its temperature's not changing. Final and initial thermal energies are the same. Well, what that means is that the external work is negative. Negative external work means that the gas is expanding. And so in this case, heat is being added to the gas, temperature is staying constant, and therefore the gas is expanding in such a way that the work done on the gas is the opposite of the heat added to the gas. They add up to be 0. So this is an example of an isothermal expansion because the gas is expanding at constant temperature. Okay. Here's an isochoric process, and for this process the volume is constant. So constant volume means no work is done on the system. W external is 0, so we draw that as a height of 0. And in this case, isochoric process means that delta W external is 0. The heat added, Q, must be equal to the change E final minus E initial in the thermal energy. So here E final is less than E initial, meaning the difference is negative, and the magnitude of this difference is equal to the heat lost by the system. So for example, in this process, the final thermal energy is less than the initial, so lower temperature. Q is negative, and what that means is that heat leaves the system, and that gives rise to a lower thermal energy. Okay, temperature decreases. Adiabatic process here, Q is 0. No heat is added or removed, so on the bar chart we make Q with a height of 0. And so what that says, if Q is 0, is that the external work must be equal to the difference between final and initial thermal energy. And here final thermal energy is greater than the initial, so the difference is positive, it's an increase, and so W external must be a positive value equal to this difference. And so this process right here is called an adiabatic compression. Compression because positive work is done on the system, which means compression, it decreases its volume, and that work goes into heating up the system. So you're going to do a homework problem on this homework on the bar charts, and we're going to be doing these more, at least in this unit. They're a nice little visual way of illustrating the first law of thermodynamics. So few more worked examples. Example of an isothermal compression. I am going to leave this as something for you to work out, and the solution is given in the notes. And we will go over this if you have questions on Monday's lecture. So I'm going to leave this to you to work out example 4. I want to go over example 5, which is more of these PV diagrams, pressure volume diagrams, as applied to different processes. So recall that pressure volume, PV diagrams, you have pressure as the vertical coordinate, and you have volume as the horizontal coordinate. And these curves here are a curve, each of these curves here are what are called these red or burgundy, reddish, pinkish curves here, are called isotherms. And so an isotherm is a plot of pressure versus volume for a process that's done at constant temperature. And since PV for an ideal gas is nRT, and we can divide both sides by V, the pressure is nRT over V, which means that if the temperature is constant and the number of moles are constant, that the pressure goes as 1 over the volume, and you get a curve which looks like this. Pressure goes as volume to the -1 power. And that's called an isotherm. It's a plot of a process done at constant temperature. Here's another isotherm, and in this case, at a given volume, the pressure is higher, and this is just an isotherm at a higher temperature. And so we can draw these isotherms, each one of these, as a line of P versus V at successively higher temperatures. We can draw curves that are higher up. Now the adiabatic curves, a curve that's done for a process as to how P and V vary with no heat added or removed, that looks like this purple curve here. And we haven't gotten to the mathematical equation for that yet, but it's a steeper change in pressure with volume. There's a steeper slope for an adiabatic curve than for an isothermal curve. And so what we want to do here is we want to see what kind of process this corresponds to if we start in a state I with a given pressure VI and a given volume VI, and we follow this curve to a final state PF and VF. Okay, so what's going on here? Well, the final volume is less than the initial volume, and so the gas is being compressed, and the pressure is higher at the end than it is at the beginning, so the pressure increases. In this case, the process is being carried out along this adiabatic line here, which means that there is no heat added or removed from the system. So in this case, there's no heat added or removed, but we've moved from an initial temperature, because we're on this isotherm down here, to a higher temperature. And so this is what's called an adiabatic compression, and no heat is added. The work done on the gas goes into increasing the temperature in the gas, of the gas. And so we can draw this as a PV, as an energy bar equation here. So Q is 0, no work, heat added. Higher temperature at the end than the beginning, so we draw the final thermal energy as greater than the initial. And all three bars on the left-hand side must add up to the bar on the right, so this W external must be positive, and it must be equal to the difference between the final and the initial thermal energy. So this is how to relate the PV diagrams here to the bar charts. And so we're going to do some more examples of those on the homework. So this concludes the first set of notes. Now we're going to go on to studying the second set, which is heat capacities and latent heats. And what we're trying to determine here is how is the heat added or removed from a substance, how does that give rise to changes in temperature, and in some cases to the changes in the phase of the gas. So this concludes the first set of notes. Okay, we're going to now be starting our second set of PowerPoint notes for the chapter. So this is chapter 19, part 2 on the PowerPoints. And again, as with all, these are located on your folder along with the videos and the course homepage. So In this, we're going to discuss what's called specific heat and also latent heat. And so, in other words, these describe how heat added or removed from a system leads to changes in temperature and phase. Learning objectives, go to these when you're done. This is what you should know for exams, for quizzes. So before we get into specific heat again, let's quickly review the first law of thermodynamics. So remember, this is just conservation of energy. In physics 1150, this Q was 0. We didn't know what heat was at that time. And so what that says is that the external work added to the system led to changes in mechanical energy, the change in the kinetic energy of the body, and change in potential. And at the microscopic level, it led to changes in the thermal energy. Now we added heat to this, we added the heat term to this equation in this chapter. And so what this says now is that we can change the energy of the system by doing work on it, compressing or expanding, or we can change the energy of the system if it's at a different temperature than the surroundings by adding or removing heat from the system. And so both of these terms have the effect of changing the energy of the system. Now in this chapter only, we've considering the case where this work done and the heat added doesn't change the macroscopic energy of the system. In other words, it doesn't change the kinetic energy of the body as a whole, the system as a whole, or its gravitational or electrical potential energies, but that all of this work and heat goes into changing the thermal energy of the system. In other words, the microscopic motions of the molecules. In other words, all of the heat and the work go into changing the temperature of the system. Okay, and this is called the first law of thermodynamics. So remember here, this equation 1 only applies if we can set the change in mechanical energy equal to 0. So that's the first law. And then the other thing that's important when you're studying for the exam and you're writing down your important equations, which this should definitely be on there, is that the sign of Q is positive. This is the heat added to the system. It's positive if Q is great, if heat is added to the system from the surroundings, meaning the surroundings are a higher temperature than the system. Q is positive, heat enters, and Q is negative if heat is transferred out of the system, meaning the system is warmer than its surroundings. Okay, W, which again the author W external is what we're calling it, but the author simply calls it W with the implication that it's the external work. The external work done on the system is greater than 0 if work is done on the system, meaning for a gas, for example, the gas is compressed. The external force is in the same direction as the displacement. And W is negative if the external work done is negative, meaning, for example, a gas expands. Okay, the displacement is in the direction of expansion, then the external force is pushing in the opposite direction, and so this is negative work. And so that's the first law of thermodynamics. And here's just the same picture again, which shows that you can change the thermal energy either by adding heat to the body or by doing work on it. They both can give rise to changes in the thermal energy. So what we want to do now is we want to be able to calculate, if we know the amount of heat done, heat added to a gas or removed, or a substance, I'm sorry, or the work, we want to be able to relate that to the change in the temperature. And we can do that by introducing this concept called specific heat. And so the heat added to the gas, work done, can be used to change the temperature of the gas. In a little bit, we're also going to consider how the heat added to a system or the work done can change the phase of the gas or the system. In other words, melting, condensing, freezing, changing its phase. And what we'll see is that it takes a lot more energy to change the phase of the system than it does to raise its temperature. So for example, it takes about 4,190 joules of thermal energy to change the temperature of 1 kilogram of water by 1 degree Celsius, but it takes over 2 million joules of thermal energy to completely evaporate that same 1 kilogram of water. So almost 1,000 times more energy is required to evaporate the water than it is to change its temperature by 1 degree Celsius. So it takes a lot more energy to break these bonds and change the phase from a liquid to a gas than it does to change the temperature. So there's an equation here which relates, so the change in the thermal energy, it turns out experimentally, a given change in the thermal energy, which is the sum of the heat added plus the external work, depends on the mass of the system, so which we denote as big M. So a larger mass, it takes more energy to change its temperature. It depends on how big of a delta T we're going to change the temperature by. So in other words, it takes a lot more thermal energy for a big delta T to change its temperature by a lot than it does a small delta T. So the thermal energy required to change a temperature depends how much we want to change it by. It depends how much mass or inertia that this system has. And it also depends on some constant C, which depends on the material. And we call that constant the specific heat of the material, or specific heat capacity of the material. Now, the change in the thermal energy has units of joules, and delta T has units of Celsius or Kelvin. Remember, the same delta T in Kelvin units is the same as Celsius, because they're simply related by an offset. So what that, and mass is kilograms, so this C must have units of joules per kilogram per degree Celsius. And what that means then is that the specific heat is the amount of energy that must be added or removed from the substance in joules to change 1 kilogram of the substance by 1 degree Celsius. Okay, and so it has units of joules per kilogram per degree Celsius. If we're dealing with moles instead of kilograms, we denote, instead of mass, we have N for the number of moles. Instead of this little c, which is the heat capacity in terms of joules per kilogram per degree Celsius or per degree Kelvin, it's joules per mole per degree Kelvin, and we denote that by a big C instead of a little c. And so some values are given here. And we see that for water, it takes a lot of energy, 4,190 joules, to change 1 kilogram of water, the temperature, by 1 degree Kelvin or by 1 degree Celsius. They're the same change. So it takes a lot of energy to change the temperature of water, but it changes very little. There's a very small change of energy required to change copper's temperature 1 kilogram by 1 degree Kelvin or 1 degree Celsius. So for example, 1 kilogram of Kelvin, if I want to change its temperature by 1 degree Kelvin or Celsius, I only needed to add 385 joules or remove 385 joules. So copper doesn't take much energy to change its temperature, but water does. And we'll see a little bit that that's why oceans with a large mass and water's high heat capacity, oceans have to add or remove a lot of heat to change their temperature. Oceans have a high thermal inertia. So let's do an example here. So we've all dealt with burning. We've all burnt our mouth on pizza. At least most of us. All right, I have several times. So if you take a pizza out of the oven and you bite into it about a minute after you take it out, or less, you're more likely to burn your mouth on the cheese than you are on the crust. Why is that? So try this. Take a bite out of a piece of pizza. Bite the crust. You're probably not going to burn your mouth. But if you bite into the cheese, you're likely to burn your mouth. So it turns out that the reason for that has to do with heat capacity. So if we look here, here's our equation. Q is the heat added or removed. M is the mass. C is the heat capacity. Delta T is the change in temperature. And so the heat added or removed so if you have a higher heat capacity, for example, like cheese does, it has a lot of water in it. It takes more heat. Higher heat capacity means it takes more heat to increase the temperature or decrease than it does the crust, which has a low specific heat. So in other words, it takes more energy to heat the cheese. It takes longer to heat it than it does the crust, but it also takes longer for it to cool. The cheese has more inertia. So when you take it out of the oven, the crust with its lower heat capacity loses heat more easily than the cheese, which tends to remain. It has a higher specific heat, and so it has to lose more energy for its temperature to change. And so that's why you will usually burn your mouth on the cheese instead of burning it on the crust. Now, strictly speaking, this is only partially true. The other reason is that the cheese has a higher thermal conductivity than the crust, and so the heat can be more easily transferred from the cheese to your mouth to burn your mouth than from the crust to your mouth. But one of the reasons is related to the fact that the cheese has a lower specific heat capacity than the crust. So here's an example. We have this is one example to illustrate why little dogs, like a Chihuahua, tend to be cold. I mean, they tend to be shivering outside, whereas big dogs tend to be a little more resistant to freezing. I mean, when they're out in the cold. So we take 100. First of all, we start with a 100-kilogram man, and we want to calculate how much energy, how much heat needs to be added or removed for the man's temperature, the body temperature, to change by 1 degree Celsius. And we're also going to calculate the same for a 3-kilogram Chihuahua, which is still bigger than some Chihuahuas. That's about 6 pounds. So express both of your answers in units of joules, and then in terms of dietary calories, which are called kcals, and 1 dietary calorie, which is 1,000 calories, is 4,186 joules. And so we're going to assume that humans and dogs have the same specific heat of around 3,470 joules that need to be added or removed to change the temperature of each kilogram of mass by 1 degree Celsius. So here, if we assume delta E thermal is equal to Q, the heat added or removed. For solids or liquids, remember that it's difficult to compress these, and so the work is close to 0, and we can approximate delta E thermal as Q. and that's equal to m times c times delta t. So in this problem, we know the mass of the man and of the chihuahua. We know the specific heat. And we know that delta T in both cases is 1 degree Celsius. And so we can plug in delta T is positive 1 degree for an increase of 1 degree Celsius. The heat capacity is 3,470 joules per kilogram per degree Celsius. And the mass of the man is 100 kilograms. And that means that the man must gain or lose 3.47 times 10 to the 5 joules of energy in order for his body temperature to change by 1 degree Celsius. Now we do the same for the Chihuahua, and the Chihuahua's mass is much smaller. It's 3 kilograms instead of 100, so m is much smaller, and when we plug that in, even assuming the same specific heat and the same temperature, we see that the Chihuahua only needs to lose about 1.04 times 10 to the 4 joules for its temperature to change by the same amount. And so that means that the man has to lose about 34 times more heat, or gain about 34 times greater heat transfer to change the temperature of the man by 1 degree than the Chihuahua. So Chihuahuas, when they go out in the cold, they don't have to lose much heat for their body temperature to change. In other words, they heat and cool more rapidly than a larger object. And if we convert that to dietary calories, using the fact that 1 dietary calorie, which is called a kilocalorie, is 4186 joules. These are 83 dietary calories, which is equivalent to about, I don't know, like a half a Twinkie or something like that, that the man needs to gain or lose to change his body temperature by 1 degree Celsius. Whereas the Chihuahua only needs to gain or lose 2.5 dietary calories for its temperature to change. So next time your Chihuahua's out in the cold and it won't go to the bathroom and you won't let it in the house and it's shivering, have a little pity on it and remember that it has a lower specific heat capacity than you do. Final example. Suppose that, the specific heat of concrete is greater than the specific heat of soil. So given this, if you have a Major League Baseball field and you have a parking lot that surrounds it and you have a sunny day, which one would you expect to cool off more rapidly at night? The field, the grass, or the concrete? Okay, so take a minute, and here's our equation, remember. The heat added or removed from a substance to change its temperature by delta T depends on its mass and on its specific heat. And we've said here that the concrete has a greater specific heat. Well, what that means is that the concrete is going to have to gain or lose more heat to change its temperature than the grass. In other words, the field, the grass, the temperature will change more quickly than the concrete. The concrete has a higher specific heat, meaning it has a higher thermal inertia, and it takes more heat lost for it to cool down than the grass. And so the answer is that the temperature, the grass would cool down more quickly than the concrete. So that concludes our notes for today. On Tuesday, tomorrow, we are going to start talking about latent heat, and we're going to see that it takes a lot more energy to change the phase of a substance than it does to change its temperature. So that concludes today. Have a good night. We'll see you tomorrow.